Okay, we're continuing our discussion of gravitation, and some interesting things we can calculate or observe here. With our formula for gravitation, that Fg equals the gravitational constant times the masses of the two objects divided by the distance between them squared. If we look at an object close to the surface of the Earth, we already know that force equals ma, and close to the surface of the Earth, the acceleration due to gravity we can call little g, so F equals mg. So we plug in mg here for the force due to gravity equals the gravitational constant times the mass of whatever. And the other object in the question here is the Earth itself, m sub e being the mass of the Earth divided by the radius of the Earth. So we're talking about the distance from the center of the Earth to the surface of the Earth squared. Well, we know that g is equal to 9.8 meters per second squared. And we can measure the radius of the Earth, so therefore we can calculate the mass of the Earth. How do we know how much mass the Earth has? We can't just put it on a scale, but we can calculate it based on g, which is known through observation, big G, which Lord Cavendish calculated with his little experiment with the masses suspended on the string with the mirror, and the radius of the Earth we can measure. Well, today we would measure it with satellites, but even before satellites, we have other lower tech methods of measuring the circumference and radius of the Earth. So with all of these things being observable or measurable, that leaves us with me, the mass of the Earth, which we can calculate. So the mass of the Earth is equal to g, 9.8 meters per second squared, times the radius of the Earth squared. I've got this in a red box here because this is an important constant to remember, 6.38 times 10 to the 6 meters. That's the radius of the Earth. And we may need to use this later on, so we want to keep this in our notes. It's also on the inside cover of your textbook. It's just a constant that you need to not necessarily have memorized, but certainly have access to. And then, of course, we've just recently introduced this idea of this gravitational constant, 6.67 times 10 to the negative 11th. We calculate that all out, and what do we get? We get the mass of the Earth. So this is how massive the Earth is, 5.98 times 10 to the 24th kilograms. And this is a relatively constant thing. There's not a whole lot of mass being added to or leaving the Earth. I suppose some meteorites might fall to Earth, and similarly we might send some space exploration vehicles away from the Earth. But the mass of those items are so small compared to the overall mass, we can generally treat this as a constant. So I keep mentioning close to the Earth's surface. The G that we've been using, G equals 9.80 meters per second squared, that's true at roughly sea level. If we measure from the center of the Earth to its edge, that radius would be the r used in the gravitational force formula. But what if we're actually a little bit further away from that? I'm going to draw a very exaggerated example here of Mount Everest. If we're sitting on top of Mount Everest, our distance from the center of the Earth has increased. We're actually at the radius of the Earth plus the height of Mount Everest, which we're going to say is 8,850 feet. No, not feet, meters. 8,850 meters. So the farther we get away from the center of the Earth, the less the gravitational force should be. Let's calculate what g, little g, the acceleration due to gravity, would be on top of Mount Everest. So mg, the force due to gravity, is going to be equal to the gravitational constant times the mass of whatever item we're talking about times the mass of the Earth divided by r squared. So mass cancels out of both sides of this equation, and we're left with g is equal to big G. So this is acceleration. This is the gravitational constant. G times the mass of the Earth divided by r squared. Well, normally the radius of the Earth is what? We just had that on the previous slide. The radius of the Earth is 6.38 million. So 6.38 million, 6,380,000 meters. But we're going to add to that the height of Mount Everest, which was, what did we just say that was? 8,850. So 8,850. So that is equal to, that's going to be 6,388,850. So that is now going to be our R, and the mass of the Earth, the problem statement said to neglect the mass of Everest itself, which would in theory have a small effect on us locally. But we're just going to say the acceleration due to gravity is equal to the gravitational constant times the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, divided by this increased radius of the Earth on top of Mount Everest, and I'll just take that to 4 sig fig, 6.389 times 10 to the 6th meters. And g, that's a constant, we know that. I should have substituted that in. G, the gravitational constant, is equal to 6.67 times 10 to the negative 11th. So we take 6.67 times 10 to the negative 11th, multiplied by 5.98 times 10 to the 24th, divided by 6.389 times 10 to the 6th, and we get a g on top of Mount Everest of 9.77 meters per second squared. So it's less. It's less than what we're used to using. We've been using 9.80 in all of our problems, and we will continue to do so. We will continue to treat this as our default value for the acceleration due to gravity. I just want you to be aware that it can change based on your geography or elevation. In this case, just due to elevation, the effect of gravity is less because we're farther away from the center of the Earth when we're on top of Mount Everest. So we can see here from this chart, the Earth isn't perfectly a sphere. The Earth is actually, it kind of bulges at its center. That's a horrible drawing, but the equator is a little bit wider than the distance from pole to pole. And that is in evidence here because at the North Pole, for instance, 9.832, that's higher than the 9.80 we're used to using. So the effect of gravity is actually higher at the North Pole because it's a little bit closer to the center of the Earth. And at the equator, it's less, 9.78, because the Earth is a little bit wider along the equator than it is from pole to pole. So we're farther away here. Also, we can see some other slight variations at Pikes Peak, for example. Pikes Peak is a pretty tall mountain. On top of it, the effect of gravity is less than what it normally would be. Denver, Colorado is the mile-high city. It's less there. San Francisco is right at sea level, so we would expect it to be really close to 9.8. New York is really close to 9.8 as well. It's 9.803. Not sure why it's the 0.003 higher, but it is based on observation. So that 9.80 that we use is not quite as constant as we would like to believe, but we will continue to use that as our default value. So let's talk a little bit about satellites. A satellite is essentially any object that orbits around another. Our moon is a natural satellite. It orbits around the Earth. The sun is, the Earth is a satellite of the sun. The Earth rotates around the sun, and we have lots of artificial satellites as well. Communication satellites, GPS satellites. All these satellites are orbiting around the Earth. The key to keeping them in orbit is getting their velocity just right. If their velocity is too low, they'll crash back down to Earth. If the velocity is too high, it will go off into space. But if the velocity is just right, a satellite is essentially always falling towards Earth, but the rate at which it's falling is equal to the rate that the Earth falls away due to its curvature. So a satellite is essentially constantly falling around and around and around the Earth. But it's falling at a very specific speed, a speed at which it never actually crashes to the Earth's surface. So if the force, the sum of forces equals mass times acceleration, and the centripetal acceleration is v squared over r, then we need a centripetal force on this side of the equation to be equal to the force due to gravity, which is the gravitational constant times mass 1 times mass of the Earth divided by the radius of the Earth squared. So this equation is true for what we call low orbit satellites that are relatively close enough to the surface of the Earth that we will consider their height, or the r value, to be equal or approximately equal to the radius of the Earth itself. Now, is that exactly true? No, of course not. Satellites don't just skim the surface of the Earth. There is some distance above the Earth, but it's small enough compared to the overall radius of the Earth that a lot of the satellite problems we look at are going to be considered low-flying satellites, in which we can approximate the radius of their orbit to being equal to the radius of the Earth. And if we take this equation then and solve it for velocity, we can see that velocity equals the square root of g, gravitational constant, times the mass of the Earth divided by the radius. So, like I said, the key to keeping a satellite in orbit is getting this velocity right. If it is traveling at just the right speed, it will stay in orbit indefinitely. If the velocity slows down, it'll crash to Earth. If the velocity is too high, it would take off into outer space. So we've got an example problem here that we will look at, but I'm going to have to start this in the next video because I am almost out of time. So we'll do example 512 in the next video.